Hello, friends. I am Satish Lele. I am a chemical engineer. I am working in field of piping for last 30 years. This video is part of my chemical process piping channel on YouTube. This video is about piping design. General considerations to be evaluated for piping design should be the design conditions such as temperatures, pressures, and various forces applicable to the design of piping systems. Design pressure of a piping system shall not be less than the pressure at the most severe condition of coincident pressure and temperature resulting in the greatest required component, thickness or rating. Design temperature is the material temperature representing the most severe condition of coincident pressure and temperature. For uninsulated metallic pipe with fluid below 38 degrees centigrade or 100 degrees Fahrenheit, the metal temperature is taken as the fluid temperature. With fluid at or above 38 degrees centigrade or 100 degrees Fahrenheit and without external insulation, the metal temperature is taken as a percentage of the fluid temperature unless a lower temperature is determined by test or calculation. For pipe, threaded and welded end valves, fittings, and other components with a wall thickness comparable with that of the pipe, the percentage is 95%. For flanges and flanged valves and fittings, 90%. For lap joint flanges, 85%. And for bolting, 80%. With external insulation, the metal temperature is taken as the fluid temperature unless service data, tests, or calculations justify lower values. For internally insulated pipe, the designed metal temperature shall be calculated or obtained from tests. The following criteria must be met for a good piping design. The piping system shall have no pressure-containing components of cast iron or other non-ductile metal. Nominal pressure stresses shall not exceed the yield strength at temperature. See Table 1049 and data in ASME Code Section 8 Division 2. Combined longitudinal stresses shall not exceed the limits established in the code. See Pressure Design of Piping Components for SL limitations. The number of cycles for variation shall not exceed 7,000 during the life of the piping system. The occasional variations above design conditions shall remain within one of the following limits for pressure design. When the variation lasts no more than 10 hours at any one time and no more than 100 hours per year, it is permissible to exceed the pressure rating of the allowable stress for pressure design at the temperature of the increased condition by not more than 33%. When the variation lasts no more than 50 hours at any one time and not more than 500 hours per year, it is permissible to exceed the pressure rating of the allowable stress for pressure design at the temperature of the increased condition by not more than 20%. Dynamic effects design must provide for impact like hydraulic shock, etc. Wind flow to exposed piping. Earthquake as per NCA 58.1. Discharge reactions and vibrations of piping arrangement and support. Weight considerations include lid loads, contents, ice, and snow. Dead loads, pipe, valves, insulation, etc. Test loads, test fluid. Thermal expansion and COMT/IOM loads occur when a piping system is prevented from free thermal expansion or contraction as a result of anchors and restraints or undergo large, rapid temperature changes or unequal temperature distribution because of an injection of cold liquid striking the wall of a pipe carrying hot gas. Design criteria for metallic pipe. The code uses three different approaches to design, as follows. It provides for the use of dimensionally standardized components at their published pressure temperature ratings. maximum stresses. It prohibits the use of materials, components, or assembly methods in certain conditions. Wall thickness. External pressure stress evaluation of piping is the same as for pressure vessels. For piping, the design pressure and temperature are taken as the maximum intended operating pressure and temperature combination, which results in the maximum thickness. For straight metal pipe under internal pressure, the formula for minimum required wall thickness mu is applicable for outer diameter divided by T thickness ratio greater than 6. For inconsistent units, P equals design pressure, D equals outside diameter of pipe. C equals sum of allowances for corrosion, erosion, and any thread or groove depth. For threaded components, the depth of age of MCP 2.1, and for grooved components, the depth is the depth removed plus 1 by 64 in when no tolerance is specified. Southeast equals allowable stress. S equals basic allowable stress for materials, excluding casting, joint, or structural grade quality factors. E equals quality factor. The quality factor E is one where the product has more than one of the following quality factors: casting quality factor EC, joint quality factor EJ, and structural grade quality factor ES 0.92. Y equals coefficient for ductile ferrous materials. TM equals minimum required thickness, in to which manufacturing tolerance must be added when specifying pipe thickness on purchase orders. Pipe with T equal to or greater than D by 6 or P by southeast greater than 0.385 requires special consideration. Thermal expansion and flexibility. Metallic piping NCB 31.3 requires that piping systems have sufficient flexibility to prevent thermal expansion or contraction or the movement of piping supports or terminals from causing failure of piping supports from overstress or fatigue, leakage at joints, or detrimental stresses or distortions in piping or in connected equipment, pumps, turbines, or valves. For example, resulting from excessive thrusts or movements in the piping. Thermal displacements. A piping system will undergo dimensional changes with any change in temperature. If it is constrained from free movement by terminals, guides, and anchors, it will be displaced from its unrestrained position. Reaction displacements. If the restraints are not considered rigid and there is a predictable movement of the restraint under load, this may be treated as a compensating displacement. Externally imposed displacements. Externally caused movement of restraints will impose displacements on the piping in addition to those related to thermal effects. Such movements may result from causes such as line sway or temperature changes in connected equipment. Total displacement strain due to thermal displacements, reaction displacements, and externally imposed displacements all have equivalent effects on the piping system and must be considered together in determining total displacement strains in a piping system. Expansion strains may be taken up in three ways: by bending, by torsion, or by axial compression. In the first two cases, maximum stress occurs at the extreme fibers of the cross-section at a critical location. In the third case, the entire cross-sectional area over the entire length is for practical purposes equally stressed. Bending or torsional flexibility may be provided by bends, loops, or offsets, by corrugated pipe or expansion joints of the bellows type, or by other devices permitting rotational movement. These devices must be anchored or otherwise suitably connected to resist hand forces from fluid pressure, frictional resistance to pipe movement, and other causes. Axial flexibility may be provided by expansion joints of the slip joint or bellows types, suitably anchored and guided to resist hand forces from fluid pressure, frictional resistance to movement, and other causes. Displacement stresses may be considered proportional to the total displacement strain only if the strains are well distributed and not excessive at any point. The methods outlined in the code are